Let's derive again the motional EMF, but from a different perspective, from the perspective of force. So we understood that if I happen to move a rod, right, in presence of a magnetic field, so as per our right hand rule, hopefully I'll be able to draw it neater. So this will be, okay. If I point my thumb in the direction of the motion, or index finger in the direction of the magnetic field, my middle finger will point in the direction of your, yes, just a second. That's better. Okay, kind of. So basically this will point in the direction of the force that a positive charge will experience. So this we understand. Now let's apply it. When we are not moving, say there is no motion, what happens? Right? This charge will be moving randomly. Again, we'll imagine a freely movable positive charge. Now when we push, right, when we push the rod, this particular charge will experience a force upward. It will aramse go upward, but creating a positive and negative space. It will create a potential difference. When I further push it, what happens? More charges will go, right? But as and when we go, we remember from our first, second chapter, as and when we have first charge, whenever we're getting the second charge in empty space, what will happen? The second charge will experience a force, a pushback. Agree? So here too the same thing will happen. Here too there will be a push downward because of our electrical field. Where did the electrical field come from? It came from the accumulation of positive and negative charges, right? So this is accumulation of positive charge. So from end to end, we have a electrical field, right? So basically, your electrical field will point in this way. So the positive charge will be getting pushed down our while our magnetic field will be pushing this upward. Agree, guys? So there is a push. There are two different pushes. Now my question to you guys is, till what point will the push continue? I have an object, two people are pushing it, and I know that the accumulation will keep increasing, right? That fact is known. So this is say Fe and this is Fb. Fb is fixed because your velocity and magnetic strength, all of that is fixed, while Fe will keep increasing. Till what point will it increase, and when will this stop? When will the accumulation stop? Again, I'll repeat the question. We understand that the charges will accumulate at one end, and so the negative charges are at the other end. And when this keeps happening, what happens? We remember from our previous classes or previous chapters that if we have one charge in empty space, getting the second charge is not going to be the same. It needs a lot of effort. If I have already 10 charges, then the 11th charge will need a lot more force to get it, right? From infinity. Same way here too, the force will keep increasing. The force that 10 charge will experience will keep increasing. Right? We'll be able to accumulate charge till the point these two are equal. Is it not? Once they're equal, a charge will not feel any force. It will feel a force, but the net force is zero. I hope I made sense. So all we are trying to do over here is get an expression for your motional EMF when we have the rod moving across a constant magnetic field, a uniform magnetic field. So Lorentz force, when a conductor moves through a magnetic field, the free electron in the conductor experiences a force due to the magnetic field. This force is given by your Lorentz force, which is Q. Sorry, this is because of, right? Let me just write the magnitude part. Since everything is perpendicular, so we end up with this formula. Let me write it a bit neater. for theta is equal to 90 degree. Here Q is your charge of the electron, V is the velocity of the conductor, and I've written it as VE, and B is the magnetic field. Okay, so let me make it as BC or something, I guess. Again, just a representation, whatever you guys are comfortable with. Next, induced electrical field. The motion of the conductor through the magnetic field induces a electrical field inside the conductor. We saw why. Charge starts accumulating. By default, we have an electrical field. This electrical field is expressed as what? QE. Right? If E is the electrical field, then the force will be QE. That's the whole funda of, right, Newton per Coulomb. Remember? That's the whole funda of your electrical field. It's a force that is experienced per unit charge. So the maximum point, the accumulation of charge continues till the point where your FE is equal to FB or FC, whatever you guys want to call it as. I think I'm calling it as FE. This is your FB, right? This is because of through the magnetic field. Yeah, correct. So basically your QE is equal to QVB. Therefore, E is equal to VB. Why? Q and Q will get cancelled and we have this expression. So this is the electrical field that is experienced inside the rod. So what is the total potential difference, or potential difference? It's not total. What is the potential difference between the end of the conductor? That will be nothing but QE. Agree? Again, go back to basic. Sorry, not QE. LE. Length into force. Force into distance. Agree, guys? Again, potential difference has to do with the force that we exert per unit charge moving from point A to point B. And so we have length into E. L stands for here the length of the rod, basically ends of your accumulation. And so when we substitute, we have VB. It's the same expression as what we derived few videos back. So this is as per voltage is equal to length into electrical field. A uniform electrical field, we can use this. So when we substitute from 1, we end up with this expression. So what can you conclude? Thus, a potential difference is maintained between the ends of the conductor as long as the conductor continues to move through a uniform magnetic field. So this is your VC, by the way. That's your velocity, velocity, and velocity. So if VC becomes 0, then this will vanish. If I increase VC, then E will increase. Your EMF will increase, as simple as that. If the direction of the motion is reverse, the polarity will obviously reverse. Okay. I hope you guys enjoyed this. I mean, I like teaching such things. I hope you guys like it too.